So it all started with a simple question. Why do we use 0.1 microfarad everywhere for our decoupling capacitors? And how did we get this number? And does it even still work? Seems like it works. We use it on everything and it works. Just how well does it work? Or is there something else we could be doing that would work even better? These are the questions I asked. And oh man, it led me down a rabbit hole I was not expecting. Oh my word. Oh, things got crazy. So we're gonna go through it. So on the bottom here, we have two of the same setup. The one on the left here is going to be our control. The one on the right is what we are going to play with. So we just have a voltage source at AC. I don't care about the voltage. So 1 volt will work. 5 volts will work. 100 volts will work. Anything. So then we have our inductance. This includes everything between the voltage source and the pad of the IC. So that's trace inductance. That is any vias you have. And that includes the ESL of the capacitor. Values you'll find for this are somewhere around 10 to 40 nanohenries. So I just stuck with 40. As you'll see, I'm being a little conservative. So the capacitor here, I just found one here in LT Spice. So that's that model. I didn't really care. My only criteria is that it had something in the field for ESR. The voltage rating I don't care about. The current I don't care about for this. In the real world when I'm choosing components, you better believe I care. But for this, nope. So on the top, what we have going on here are two graphs. Right now they look the same. So red is going to be our control. This you might recognize as an impedance graph. Over here is our impedance measured in ohms. Down here is our frequency. So just a crash course. When it comes to reading these, capacitance dominates all the way here on the left. Inductance dominates all the way here on the right. And when they come together, it's a resonance. Now we have all that, we can play. So, as I said before, 40 is a high number, 10 is a low number. So what we'll do is, let's just try 25. Let's see what happens. We'll run this again. So if we take a look here, gotta fix that. You need cursor numero 1. Move that out of the way. So if you look at that, our low frequency stuff, nothing. But the impedance of our higher frequency stuff went down. Cool, cool, cool. How much? Let's just go to about 20 megahertz, 19, that's good enough. Went from 4.75 ohms all the way down to just a little under 3. So that's kind of that's not a lot of inductance. That makes a good bit of difference. So if we go down to 10, we do all the things right. Oh boy! 4.75, 1.13. So as you'll see when we get to the math, that counts. That does count. Okay, so let's set this back up to 40. Actually, no, I changed my mind. Let's just, what happens if we go, we really screwed up, man, and we go up to 100. All right, Just making sure it goes up higher. Okay, let's switch back to 40. All right. Now, what happens here if we make this go up? So let's go with 6.8 microfarad. And let's just pick one in the list. Look at there. High frequency stuff doesn't change at all. But low frequency, holy moly. Where are we at? 7 kilohertz? We go from 221 all the way down to 3. Wow. Okay. Well then. Now let's see what happens if we go the other way and if we go really low. Let's go to 1 nano. Here, let's pick, yeah, that one will work. All right, well, our low frequency stuff turned terrible. However, look at the right side of the graph. Check that out. We're at a huge difference between these two for capacitance, but at higher frequencies, around 100 megahertz or so, about right here, 50, 60, same thing. So at around this point, lower values don't do jack. It's like they don't even exist. But at the lower frequency end, oh boy, they make quite a bit of difference. Okay, one other thing I want to check is, actually, you know what we're going to do? We're going to take that out. We're going to bring that one back. Then what we're going to do, we're going to take that going on there. That's probably a good thing to do anyways. Let's see what happens when these two are in parallel. Run! All the things are lower. Makes sense to me. These are in parallel, so that goes under. These are in parallel, so these go up. So, half the inductance, twice capacitance. Alright, makes sense to me. Now, let's see what happens if we do 4.7 microfarad in two of these. Okay, the reason I chose these, a lot of ST micro data sheets have you do this. They don't tell you why, they just say, just do it. Let's check that out. Ooh. Okay then. So right here, we have a resonant peak. Now, whether that's good or bad, we'll get to that. But this is a strike against mixing values. You have to be careful if you do that. Make sure your resonance is not too high. Okay, something to be aware of. But overall, if you deleted this from your mind, we're doing quite a bit better than just 0.1 all by itself, both in the low and the high frequencies. But if that peak gets too big, could be bad. Okay. So all in all, less inductance is better for the high end. Higher capacitance is better for the low frequencies. All right then. Two things I am not mentioning until now is I started this at 1 kilohertz for a reason. Between 0 and 100, your voltage regulator will take care of those. Those will be very low. And that kind of makes sense because you want your voltage regulator to have low impedance at DC or close to it. At your high end, plane capacitance, assuming you are using a ground plane, you better be. plain capacitance that's built into the IC. That'll take care of the high frequency stuff. Now, we get to do the math, because pretty pictures don't mean anything if I can't tell you where we're supposed to be at on the graph. So, time for some math. Oh yeah! Okay. So, the first, we got a few formulas. None of them are a big deal. So, I'm going to skip this K value for now. So, a formula to figure out what our impedance should be. So, VDD, so just an example, we're just going to use 5. Ripple percentage, I've seen 3 and 5 be used, percent. 1%, yeah, I've seen that too. I think 10% could work in this case, because it's only 0.5 volts. That's not going to change. It's digital signal. It's not going to change anything. But the reason why I think 0.5, you got to remember, digital signal, you're going to be at 0 volts and have noise that goes into a negative voltage, which ICs don't really like all that much. But your fancy 8T Mega 328P will take minus 0.5%, or 0.5 volts, so we can do 10. Transient current. Well. This is where you're going to have to know your circuit. You're going to have to know what's going on in order to make this determination. So remember, it's not DC current. It's you switch something on. So for this example, I'm just going to assume a couple LEDs. Okay, this K value, just use 2. You can go less if you want. Don't worry about it for now. So I want to show you our targets. All right. So I found another formula, because you're going to need a bulk capacitor for those really low frequencies. So the formula, remember I said 1 kilohertz is fine. So if you target that, that becomes 160 microfarads over your target impedance. So it's pretty easy to remember. So in this case, we've got 64. So let's go back. Okay, now what we're going to do is we're going to go back and to our original. All right, 2.5 puts. Hey, what you doing? There we go. 2.5 goes right about, yeah, right there. But hold on a second. Hold on. 400 milliamps? If you're doing an Arduino ATmega 328P, it can only do 200 milliamps. At 400, you're going to blow it. No siree. If you have enough LEDs to do, that's a Christmas tree amount of LEDs. No siree. It is 0.04. 40 milliamps. There we go. Now we're talking 25 ohms. All right, let's go up there then. So we're at 25 ohms with the crappiest connection to our IC you could have. I suppose you could do worse, but you'd have to try. We don't want to try. So right now we're at 62 kilohertz. And over here we're at 100. So your question is, wait, what's going on? Is this 100 okay? Well, if we go back, we look at this formula. So I had to look online for the rise time for these AT megas. 8 nanoseconds seems to be what the internet said. And we all know you can trust the internet. But by golly, man, let's just do it. So your bandwidth here is described as 0.35 over the rise time. Now, if you look online, you'll quickly see this is an approximation. It's not some exact thing. If it was some exact thing, I'd be a lot more gnarly to write than this. But if you look, it's a pretty good approximation. So if you really want to be safe, 0.4, 0.5, but 0.35 is pretty darn good. Another thing I want you to notice, this is not 16 megahertz. This is way above. So your bandwidth is determined by the rise time, not by the clock frequency. So 40, round up 44 is what we're looking at for the high end. So, and we've got 100. So to answer the question, is 0.1 still a good value this day and age? I mean, that looks pretty good. I mean, there's some stuff over here that's not getting taken care of properly, but by and large, this ain't half bad. And if you get your inductance taken care of, you can get that high frequency stuff made even better. And you know what? Let's go back. And take a look at ST's recommendations. Put this back at 25. I'll get there. All right, that's pretty good. Okay, so if you see, so our resident peak, we're still underneath it, so we're pretty good. So ST might be onto something with this recommendation. So, but look, what's our target bulk was 6.4. So, yeah, 4.7, that's pretty good. So, you know what? How close can we get to 6.4? What, 6.8? Yeah, 6.8. Let's double check, make sure everything is good. All the way over here. 23, yep. The math does check out. So let's go back over to the formulas. Okay, so I was going to talk about this K value here. You're not going to see that much place else on the internet. I had to get it from Henry Ott's book, and holy moly, confirming that was a nightmare of math. Okay, so the story behind the K value is that your noise, we only care about the noise in this bandwidth right here. Anything higher, we don't care about. So what he was saying was that approximately half the noise energy is going to be outside of this. Hence, you can double your impedance target. Half your impedance target. Double. Okay, but you know, with all this stuff, you know, data sheets say 0.1's okay, or other people are saying, to hell with the data sheets, use the biggest capacitor. With these guidelines, I'm checking them. So the formula to figure all this out is nightmares. The stuff of nightmares. I'm out of school. I don't want to deal with signs. But I did it for you. And what we found out is that, keep in mind, we have 16 megahertz. This is, you need the third harmonic to get this. And if you find out, the you look at the first three harmonics, most of the current is in the first three. So in everything after that, we just pretend it doesn't exist. It does, but it doesn't contribute much. So what I found out was that 2 was close, but not quite. So what I found was 1.91. This assumes a 16 megahertz clock and 8 nanosecond rise time. So I couldn't help but take the liberty of, technology's getting better and better. And there's nothing precluding the industry from saying we want a 16 megahertz clock, but with a 1 nanosecond rise time. So if you look at this, first off, we go to 350 megahertz. So did this get there? Here, let's get this. How far do we actually get? We're getting to our 25. All right, 200 megahertz. So we're going to have to definitely decrease this inductance. Or alternatively, as you saw, put more 0.1s and stuff in parallel in order to make that happen. So that, just doing that rise time might actually break some circuits because of that. Because your boards aren't designed for that. At least in the 16 megahertz era. But back to the harmonics. If you notice, it is now much more spread out. So if we sum those all up, 61%. That's a lot more than the 50% assumption than that was being made. If you do equals 1 over that, 1.64. That ain't 2. So 2's probably okay. It'll get you in the ballpark. And it creates these nice smooth numbers here. But you know what? I'm actually cool with it. Put that back to 8. So we can see, yep, most of the energy. First 3 harmonics. All right, so what have we learned today? We've learned some formulas. We've learned some graphs. Go small in the inductance. Go big on the capacitance. Definitely calculate your impedance target. And follow the impedance target. Love the impedance target. And calculate what you need for your bolt capacitance and do it. Oh, one other thing. Let's go back here. One thing I didn't think about. Actually, no, I'm not going to delete anything. Sometimes a lot of what people do is you need a bolt capacitor and it needs to be huge. Okay. I want to list all. We have any... Okay, that'll do. Now let's do that. All right, see, when you go big, you go, whoa! However, what I'm looking for is... Ah, shucks. You know what? Here, let's go 100. See, this is what I want, but I'm not too keen on... Hey! All right, never mind. What I was hoping to do is make that resonant peak huge. And it is just not happening today. Not with these values anyway. That did not happen. Okay. It is not happening today. But sometimes what you can have are those resonants go huge over your target impedance. So how else can we play with this? 40 milliamps. Let's say you wanted to go, you just wanted a one size fits all. So for your 18 mega, you can only go to 0.2 per data sheet. That's as much current as you can do with that. And that 10% ripple, it's fine. But you know what? We can even go to 5. And that K value, bring that back down to 1.9, which is what we were seeing. If you get down to 2.4, so holy smokes. Here, let's just get that. Now we're done with this. Let's just get rid of this. All right. Does that 2.4 go? Okay, that gets you between 2.5 megahertz and about 10. No dice! What we can do is go back, get that bulk capacitance in. Let's just go with 100. Oh, 100U. Let's go ahead and do that. Ah, there we go, the resident peak. This time it's huge. 4.75. Not acceptable. So here's how to fix that. This is what I wanted to show you. Okay. We need to show all. Now what I'm looking for is an electrolytic. Alright. So check this out. Big ESR compared to before. 0.59. Oh, look at that! So this is why sometimes you want an electrolytic. Because this high as hell ESR smooths out. It dampens those bloody peaks. Nice! Okay, so what are we here? Oh, snap! 2.4? Okay, at the low end, we're good, baby! Okay, I guess 211. We still suck. Alright, but you know what? That's actually, 2.4. Wait, we're at 2.4. Good lord. Okay, we're over 100 megahertz. We are fine. This is perfect. This is pretty flat, which is awesome. So, problem solved. This will last a long while. You could do this for these specs. For your Arduino, you are fine. This will work for any project that you have with that. So, provided you're not screwing it up. So, I think what the original question is point one even a good value? Yes, but we can do better. And we should do better. We're engineers. We want to design our stuff to last. We don't want some weirdo change to an IC like a rise time change, which is only getting faster. We don't want that to screw up our designs. I can tell you, I've seen it firsthand. It is a pain in the ass to figure out because nobody's going to tell you, hey, our IC's got a faster rise time now. You might want to check that. No, you're just going to get the IC in. People are going to say it doesn't work. And you're going to have next to no idea. It's going to take you a long time before you ever think, maybe they changed the rise time. It'll take you forever before you think, maybe I should scope this line and see what's going on. And it'll take you forever before you think, should I look at the rise time? So if we design our circuits to be very resilient in the first place, we save ourselves a ton of time. So all of this here, so final thoughts, all this here blew my mind. So I thought we should be able to calculate this. Don't just give me guidelines. I should be able to calculate this for myself to figure out if it's good or not. Like, these should be in textbooks here. I shouldn't have to scour the internet or go read every book in the world to figure this stuff out. This is basic stuff, man. Decoupling. If you don't decouple, your circuits won't work. Or if they do, you're lucky. So, another thing I just want to point on, capacitors have come a long way. Also, our layouts are better than ever. So, that's part of the reason why this still works. So, point one has been used for 50 years, but multi-layer ceramics, they have not been around for 50 years. Surface mount, they didn't get popular. It wasn't a thing 50 years ago. But if you're not doing it today, you've got good reasons. So I think between this and all the formulas, I think you've got enough here to make an informed decision about what decoupling capacitors and bulk capacitors to use and how to calculate all this stuff. That way, your designs can be better than ever. This is Steven, signing off.